to transfer a signal from one port into another port. Transistor. Okay, it has two types, NPN and PNP transistor. And we know transistor has three terminals. Transistor has three terminals. But how many terminals we need to make transistor as a amplifier? Or basically any network or circuits, basically any network or circuit, how many terminals needed? Generally 4 terminals. How many terminals we have? Only 3 terminals. So with that constraint, we ourselves decided one terminal as a common, or we as decided one terminal as a common, or we make one terminal as a acted as an input as well as output unit. Okay, it means common. So in that fashion we derived the 3 configurations. So configuration state that with the help of 3 terminals we could derive 4 terminals for the effective usage of transistor as amplifier or as switch. If transistor obeys the linearity, then each transistor can be a amplifier. If transistor does not obey the order of linearity, then the transistor can be act as a switch. Simple on-off switch. Okay. So the configurations are 3 configurations: common emitter, common base, and common collector. Last class we made attempt to understand common base configuration, right? So in that we understand input characteristics. What is input characteristics? It is a curve or a plot or a graph which relates input current versus input voltage at output voltage constant, or it shows the relationship between emitter current and emitter to base voltage. When I am executing input characteristics, I know that the output parameter must be constant. Why? Because I need to see the relationship between input voltage and input voltage and input current, which sense, what do you mean by that? The output parameter should be constant, or else my input sometimes may influence the output current, output voltage. My input voltage may influence the output current. So it is compulsory that we need to make output parameter as a constant. I have derived that one. Okay, okay. Please welcome, sir. Please welcome. So I welcome Dr. Sendil Kumar sir. Okay, now listen with that. Sir, talked about IET society. Okay, it has a lot of benefits. Technically, you will contribute. Later, we'll have a discussion about that. Now, we'll move on to common base configuration. Listen, last class we have concluded about what is output characteristics. Now, I need answer from your side. So, I made incomplete in this diagram. I made incomplete. What is that? I have to mention the potential, right? That is voltage across base to emitter, voltage across base to collector. Here the base is common and collector is my output, emitter is my input, right? What I have drawn on the board? I have drawn output characteristics of the given common base configuration. Why common base? Base is common for both the input and output, right? So what type of transistor is this? This is a NPN. What is the function of emitter? Emitter has to emit the, collector has to, yeah, got the point? Here, this has to be repulsion, repel the majority carrier. Here, I need to attract the majority carrier. So, what is electron? Negatively charged, right? So, negatively charged, what should I draw here? Positive or negative? Positive, right? So, positive. Okay, so this has to negatively repel same charge. So what should I? Okay, you got the point? This how you mean you could remember the polarity of the external battery, right? So how many batteries are required? Two batteries. How many junctions are there? Two junctions. So remember always base emitter junction is forward path and collector base junction is reverse path. What is the function of base emitter? Gavani. What is the function of base emitter? The base emitter junction always helps the majority to cross the junction. What is the function of collector base junction? Again, it collects the majority carrier. Got the point? See, the base emitter junction used to make the majority carrier to cross the junction. Collector base junction make the minority carrier will cross the junction. I'll repeat. Base emitter junction are generally biased such that it is used to help the majority carrier to cross the junction. And collector base junction biased such that it is used to help the minority carrier to cross the junction. So what is the function of collector? Is to collect the majority carrier. What is the function of emitter? Is to emit the majority carrier. So emitter is always highly doped. Collector is moderately doped. Okay. In that concept, I'll draw on the diagram. Now, come to the point of understanding this one, right? Output characteristics. There are four regions, right? In generally, how many regions? In general, if question paper asks you, how many regions? You remember that active, saturation, and cutoff, right? I'll tell you in deeper, right? The fourth region is also there. We never ever record the information. Why? This is not recorded region where the device got damaged. Permanent damage occurred at the junction. Okay, which means the transistor lose its originality, NPN or PNP. So once the damage caused by the over voltage, that over voltage makes over kinetic energy in terms of thermal energy. So that huge heat will melt the PN junction format. Okay, so breakdown will be it's a forbidden state of understanding that device gone, and there is no recorded information where I can use INC to draw the graph, right? These are all the forbidden gaps. Now, what is cutoff? The cutoff region merely it is very near to the horizontal axis. What is the horizontal axis? 0. Listen. Y axis represents current, listen all of you. If there is important is there in right, do you feel anything important than this class? I'll request you to please go and have a discussion, complete your whatever right, you come back. I'm waiting for you. Okay, so y-axis represent current, x-axis represent voltage. Mean in y-axis, what is the voltage value? 0. In x-axis, what is the current value? 0. So see, this region is near to, this shaded region is near to horizontal x-axis, which means that there is a minimal amount of current or leakage current flows across the junction. Okay, and what is this? Y-axis. What this axis represents? Maximum current. What is the voltage drop? Almost 0 or less than that, minus. Okay, so this region represents saturated current or maximum current at the lower voltage. Now what is this? Active region, right? So the active region represents, it is in between cutoff and saturation. So in the active region only, your device can be a linearly responded, linear response obtained in the active region. What is breakdown region? Which is the region is beyond the active region. If I keep on increasing, yesterday we have made an attempt to, day before yesterday we made an attempt to track the VI characteristics of the common base configuration. There we understand that almost, even I kept greater voltage 1, 2, 3, 4, 5, I could find almost constant. But some batches exactly this slope will be slightly like this, slightly right, like this, which means here it might be 1 and here it might be 1.1. So there's a change that happened because of this slight change. But voltages keep on changing, 1, 2, 3, 4, 5, 6 goes. But what about current? 1, 1.1, there's a small change. Okay, that change we recorded as a dynamic resistance. Change in dV, right? Change in dV with a change in del I. So dV by di, that equal to small r. What is small r? Dynamic resistance. The smaller letters always represent in any circuit theory, electronics theory or whatever, any book irrespective of A to Z author, they wrote books, right? They have used lot of notation, especially if you find a smaller letter, small a, small b, if anything find small, then that closely associated with the omega, which means frequency change in AC signal. If anything you find capital A, capital B, capital C, then you understand that F is equal to 0, that is called DC. If you find capital letter, you understand DC signal. If you find small letter, you will understand change in parameter with respect to omega, 2 pi f. Okay, so this is what about the common base configuration, what we had last class about the output characteristics. Got the point? Now take down the general, in general, transistor equation, transistor equation, IC is equal to minus alpha IE plus ICBO, open bracket, 1 minus e to the power of Vc divided by Vt. In general, transistor collector current is equal to minus alpha into IE plus 1 plus beta, sorry, ICBO 1 minus e to the power of Vc by Vt. Now, what is IC? Collector current. What is IC? Collector current. Again, I'll repeat the sentence. There are 100 electrons start from the emitter. Only 99 have reached to collector. 1% stored in the base. Okay. So this is 99% of the output current. This is 100% of the emitter current. And what is the alpha? Alpha is the ratio of IC by IE. You always remember that these three parameters, okay, alpha is equal to IC divided by IE, beta is equal to IC divided by IB, and one more parameter, strongly say. So these three are the transistor parameters. If you go and take any transistor, these three are the fundamental, look like a birth certificate. You got the point? Look like a birth certificate, right? So what is alpha? IC by IE. What is beta? IC by IB. VBE is equal to 0.7 for silicon. How do I remember? Just draw the symbol like this. Okay, emitter, collector, base. So ratio of this alpha, what is the ratio? IC by IE. Ratio of this, okay, IC divided by IB. What is the junction? PN. PN have the barrier potential of 0.7. Okay, so in the anti-clockwise format, I could remember this way. What is alpha? IC by IE, approximately 1, approximately, because 100 electrons started, only 99 have reached, less than 1 got recombined or settled down in the base. What is beta? What is beta? IC by IB, right? So what is IC value? You know that, right? Milliamps collected. So what is VBE? Again, you see that capital V, capital B, capital E. This is constant. This is constant. What do you mean by constant and variable? You know, right? Variable varies with respect to some parameter. Constant is always remain constant. So capital V, B suffix E equal to 0.7 for silicon. Again, the 0.7, I'm saying theoretically it is 0.7, but varies between border, right? Like 0.699 to 0.7111 something, right? So this is what. Now, what this minus represents, IC and IE current flows in opposite direction. You remember, this shows the 180-degree phase shift. You remember this point, I'll explain in later class. Got the point? You remember this, collector current and emitter currents are flows opposite direction. Okay? Okay, I'll tell you, literally I'll just tell you, just to try to understand that simple way. So there is a weak signal as my input, VI, right, connected back to common emitter, right? This is load and this is my source, right? Okay, for simple understanding, I'll take you in detail in later class while taking analog circuits one. But this is out of scope, but try to understand. In book, they are not given enough explanation about why the minus. They said only opposite direction. They mentioned only one word, IC, IE are flowing opposite direction. I'll ask you one question to all of you. Listen to me. IC, IE, in the, you find opposite direction? No, but in the book they mentioned. What they mentioned, it is correct. What you see, it is also correct. Now let me explain. Both are look like a complex conjugate, but remember, I'll explain to you. Don't worry, right? So, whatever the book said, opposite direction, absolutely correct. Whatever you see in the diagram, same direction. This is also correct. Remember, the book says IC, IE, opposite direction with respect to the amplifier circuit. And this common base is not opposite direction. Both are correct. Both are correct. Let's say, let's find it. See, what is this? 10. Okay, before going to this, resistor 1, resistor 2, what is Kirchhoff voltage law? Potential rise is equal to potential drop. Fifth bench, violet color shirt, blue shirt. Violet shirt, blue shirt. Somebody disturb பண்றீங்க. இந்த கண்ணாடி கவனி. ஓகேவா? So what is Kirchhoff voltage law? Potential rise is equal to potential drop. What is that? என்கிட்ட 10 ரூபாய் இருக்கு. எப்படி செலவு பண்ணலாம்? 5 plus 5. எப்படி செலவு பண்ணலாம்? 1 plus 9. அப்படி இல்லைனா 8 plus 2. You got the point? Potential rise is equal to potential drop. Last class also mentioned cutoff region, active region, saturation region. In that I have clearly mentioned 3 volts is the input given. How much we took? Maximum of 3. Not beyond that. Then beyond that, this could happen. Breakdown. Okay, wow. So 10 volt given. Let's say this is resistor 1 and resistor 2. If both are equal, how this separated? This can be splitted by 5 plus 5. If R1, R2 are equal, then this is potential rise. These are all the potential drop with respect to plus, minus, plus, minus. What is this? Battery, right? Plus and minus. What is that? 10 rupees. It's divided equally. Why? R1, R2 are equal. Now the same concept, let's say, what is the voltage given? 10. What is the drop? Let's say 2 volt is taken across. What is the remaining? Remaining should be appeared is look like this, right? This is collector, emitter, resistor. So 2 plus 8 equal to 10. That is called Kirchhoff's voltage law. Let's say during positive half cycle, what is amplifier? Convert a weak signal into strong signal. Small change into large change with 180-degree phase shift. Right now. So what I'm trying to say, during positive half cycle, the base current increases. Positive half cycle. What is that? What is that? Positive half cycle. What happened? Increases, right? So base current increases from 0 to, let's say, 1 volt. Okay? Increases. Collector current is also increases because IC is equal to beta times IB. IC is equal to beta times IB. How many times? 99 times. How many times? So microamps into milliamps. So collector current is also increases. Then what about collector drop? There is a resistor. Voltage drop across increases. How much I have 10 rupees. What is I spent? I spent here, I spent 2 rupees because collector current increases, voltage increases. What about remaining 8? You see that the voltage drop increases. Now the current is flowing from base to collector. You got the point? And the current now here delivered to this way, right? You see that current flowing from like this. Current flowing from like this. What is this? Like this. See, this current flows from this way. This current flow of, or you understand that current flow from top to bottom. This current going bottom to top. This is IB. This is IC, right? This is IB and this is IC. That's why they said opposite direction. 180-degree phase shift is always obtained in the common emitter configuration. That is based on this. They mentioned minus represent IC, IE are opposite direction. But here it is not the case, right? So it is understood. It is derived, well derived. If you take any book, it is well derived based on the real-time circuit. Okay, this is for the exampulations or example. No need to bother about this. Now take down the first equation. What is first equation? In general, collector current is equal to minus alpha IB plus ICBO. It's a take down leakage. ICBO is a leakage current. ICBO is a leakage current with base open. ICBO. What is ICBO? ICBO is the leakage current with the base open. With the base open. Leakage current. LEAKAGE. Leakage current. CURRENT. Leakage current with base open. Okay, wow. Okay. So listen. Now what is VC? VC is the applied voltage. And what is VT? It's a what is VT? Volt equivalent temperature. What is the exact value? So VT exact value is given 25.7 millivolt. What is that? VT value always 26 millivolt, approximately 26 milli, 10 to the power of minus. But what is this? Applied voltage. How much voltage? I'm sure it is greater than 1. I'm sure it is greater than 1. What is 1? 1000 millivolt. What is 1? 1000 millivolt. What is VT? 27. Who is stronger? 1 volt is stronger or 25 millivolt is stronger? Yeah, got the point. So VC far greater than VT. Now, what happened to this? This become 1. So IC is equal to minus alpha IE plus IC I suffix capital C capital B O. Okay, ICBO. So let's say this is equation number 1 and this, let's say this is equation number 2. Okay, third one. Relation 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 among AMONG relation among IC, IB, and ICBO, I suffix CBO, I suffix. Okay. So now from this equation, we have to take this equation. So you mentioned here the minus negative sign in above equation. In above equation, the negative sign indicates in above equation. Negative sign indicates. Negative sign indicates indicates that IC current, IC and IC and IE are in opposite direction. IC and IE are in opposite direction. Now IE equal to minus IC plus IB. 100 is equal to 99 plus 1. Okay, next line. What is IE here? Just substitute, right? What is this? IE. Substitute this value in above. Substitute equation 3 in 2. What happened? IC is equal to minus alpha open bracket IC plus IB close bracket plus IC BO. Yeah, minus into minus plus. Minus into minus plus. Okay, next line. Next. IC, just copy down. Minus alpha IC is equal to alpha IB plus IC BO. IC BO. Now this IC open bracket 1 minus alpha is equal to alpha IB plus IC BO. Okay. So IC is equal to alpha divided by 1 minus alpha into IB plus ICBO divided by alpha. This is equation number, okay, let's say 4. Let's say 4. Okay, what is beta? I think last class alpha divided by 1 minus alpha, right? So what is beta? Beta is equal to alpha divided by 1 minus alpha. Okay, now just rearrange. Yeah, rearrange this. This could be rearranged by beta divided by alpha. This could be rearranged by beta divided by alpha. That is equal to 1 minus this alpha come back, right? So what is beta? Beta equal to alpha divided by 1 minus alpha. What is here? Alpha divided by 1 minus alpha. Take this into here. So what we have? 1 minus. Just rearrange this. We got it. Beta 1 minus alpha, that equal to alpha, and beta minus, just rearrange, beta alpha equal to alpha, and finally we have got it. What we got? That beta is equal to alpha open bracket 1 plus beta. So that is equal to beta divided by alpha is equal to 1 plus beta. Beta divided by alpha is equal to 1 plus beta. I see. I'm sorry, 1 minus. Yes, 1 minus alpha. Right? So you just replace this. How to replace? Alpha divided by 1 minus alpha. Yeah, you replace beta equal to 1 by, just rearrange. You got it, 1 plus beta. You take down, you will understand. IC equal to, don't worry, I'll explain, don't worry. Now the final equation is that, you will understand. Next to that, what is this? IC is equal to alpha divided by 1 minus alpha into IB plus ICBO divided by 1 minus alpha, right? So after rearranging this, you might have got 1 plus beta into ICBO plus beta into IB, that is equal to IC. You just rearrange this with the beta. What is beta? What is beta? Alpha divided by 1 minus alpha. Okay. What is here? You got the point? Yes. Just rearrange. You got this IC equal to 1 plus beta IC. Now, next topic. Transition capacitance. Title: Transition. TRANSITION. Transition capacitance. Transition capacitance. Yeah. Transition capacitance. Space charge capacitance or transition capacitance. Space charge capacitance or space charge capacitance or transition capacitance or depletion capacitance or barrier capacitance. BARRIER, barrier capacitance. Space charge capacitance or depletion, DEPLETION, depletion capacitance or barrier capacitance or transition capacitance, generally denoted as T, transition capacitance. Generally call it as TT. Okay, take down the diagram. Yes. Just take down the diagram. Monk. Take down this one. Take it down. This diagram. So P type, N type semiconductors. P type, N type semiconductor. So I have not marked a junction. I marked like this. Okay, listen and take that. Initially, I took a piece of semiconductor. Listen, all of you. Listen. We have a time to discuss. I have taken a piece of semiconductor. The conductor name called N type. Right? I have taken piece of semiconductor. The conductor name, piece of semiconductor name is N type. Right? Listen. Piece of semiconductor. Right? I have taken a piece of semiconductor. The name called N type. In that, one smaller area I have chosen and I have applied a indium metal. Look like a tri-covalent bond metal and spread like this. Spread like this. I'll repeat the sentence. This is called alloy junction or fusion junction. Alloy or fusion junction. How this alloy and fusion junction has to be made? This has to be followed like this. First, I like to take a piece of N-type semiconductor. Look like this. Look like a chocolate bar. Fully completed with the N-type. Full of N-type choco. Now, I spread indium. Indium is a metal. I have not taken boron. I have taken an indium. It's a metal. It is a metal. The two trivalent covalent ball metal applied or spread. Look like deposition, right? Spreading, right? Deposit over the some area at high temperature. At high temperature. So the temperature would at high temperature, what is that high temperature? The temperature is greater than the melting point of the indium. I'll repeat the sentence. I took the bar. It is called N-type semiconductor. It is an N-type semiconductor. In that, I spread the particles called diffusion particles. The particles name called indium. Indium is a type of trivalent covalent bond. I spread. And after I spreading, I have applied a higher temperature. The temperature normally greater than the melting point of the indium. Once I applied a high temperature, then what happens? This indium makes diffused into N-type and forms the region. That region is called P region. That region is called P region. That P region I have taken here. Let's assume that the region P and region N are equal. Let us assume that region P and region N are equal. Okay. And what is this ND? ND is the charge density, right? Charge density at N region. What is the charge density at N region? Normally a electron. What is the charge density at the P region? Normally holes. Okay. Or normally holes. Okay, now come to the point of understanding. Up to this, any doubt? Up to this, any doubt? I've taken a bar, I spread the indium, I've applied high temperature, which is normally greater than the melting point of that indium. Now, the region which is exposed by a high temperature, highly elevated temperature indium is converted into p type. Now, the N region normally rich in electron shows the higher elevated region, and P region normally shows very low charge density but wider, spread wider. Now, what I am assuming that both P region and N regions are equal by means of concentration. What concentration? Charge density, right? You write here charge density. Above this charge density, right? I'll tell you charge density. Now listen. The width WP is the width of the charge spread across the P region, and Wn is the width of the charge or ion across the. You see that both are happened exactly at the junction. Both are happened exactly at the junction. Okay, now what is the explanation for this two undivided portion? Now let's say P region and N region. We know P regions are rich in holes. When P region crossing the holes, it becomes negatively charged ion. Again, N region losing electron. Now it become a positive ion. Okay, so this become positive ion. This is called depletion region. This is called depletion region. So this is happened at open circuited. This has been done at the voltage equal to 0, or applied voltage is equal to 0. Okay, applied voltage is equal to 0, which is normally happen. So this region called depletion region. What I'm talking? I'm talking about transition capacitance and reverse bias. Transition capacitance at reverse bias. Okay, fine. Okay, now at open circuited, you understand that both the regions are share their majority carrier, because why this negative ion? It loses positive charge. What is positive ion? Loses negative charge. Initially both are equal, but the transition capacitance happen at the reverse bias. What is reverse bias? Please stand up. What is reverse bias? Okay, I'm sure you don't know the answer. Okay, what is reverse bias? You know, majority carriers are moving away from the junction. What is forward bias? Majority carriers are moving towards the junction. What is transition capacitance? Transition capacitance exists or induced or indulged at or under reverse bias. So under reverse bias, what happens? All the majority carriers are moving away. All the majority carriers are moving away. I would say there are uncovered majority carriers are moving away from the junction. What is reverse bias? There are uncovered, uncovered majority carriers are just now drifting away from the junction. Okay, all the majority carriers are moving away from the junction. So what happened? This depletion region keeps extending. This depletion region become widening or become wide. Wide means right, in reverse bias. You know that this depletion region is always has the ability to stop the charge carrier. Mean depletion region, I would say it is a dielectric component. It looks like a dielectric component. So under reverse bias, depletion region keep extend like this. When the depletion region keep extend, why this keeps extend? Because all the uncovered majority carriers are just move away. So I just want to study this capacitance called transition capacitance. Okay. Okay, sir, you have explained it, but I want to know what is capacitance. Because we are being a first year students, I don't know what is charge, what is capacitor, what is capacitance of the capacitor, I don't know. Now I'll explain. Listen, this is purely belongs to a subject. and this could be your basic, right? Right, listen. What is capacitor by physics? Physically, physically, how capacitors look like? The capacitors are two conducting plates separated by dielectric. What is that? Two conducting plates separated by dielectric. It is called capacitor. Plate A, plate B, and terminal A, terminal B separated by a paper or mica or insulator, oil, etc. Two plates separated by dielectric called capacitor. What is called capacitor? What is capacitance? This is definition for capacitor. What capacitor? Two parallel plates separated by a distance, even by r, even by r. Got the point? Got the point? Capacitor. What is capacitance? Now, now listen. What is this? Charge. What is this? Let's say positive charge. Now I'm trying to give an explanation about capacitance. CE, right? CANCE, capacitance. What is this? Capacitor, COR. What is capacitor? It is a component, passive component. Why passive? I'll tell you later. Component. What is this? Capacitance is the effect of capacitor. What is capacitance? Is the effect of capacitor. What is that? Now come to the point of understanding. There are charges. Let's say this charge, static. Charge static. What is that? Charge static. So the charges are look like have its own flux around the charge, right? With the distance, with the unknown distance, with the unknown distance x. Let's say this is static charge. It has electric field of E. Right? What I'm explaining, I'm trying to explain capacitance. What is this? Capacitor. What is capacitor? Two parallel plates separated by a dielectric. What is the function of capacitor? These two capacitor, if I connect some battery, look like this, minus and plus, what happens? This hold all the positive charge in one side, this hold all equal charge, 5 plus 5 minus. 5 plus 5 minus. So, what is the basic function of capacitor? The basic function of capacitor is to store electricity by means of charge separation. Store electricity by means of charge separation. What it stores? It stores static charge, which means electricity, which means electric field. You got the point? So, what is the function of capacitor? Capacitor normally allows the charge carrier when the charge carrier have its own frequency. For example, if it does not have any frequency, look like DC, negative potential connected to this plate, positive potential connected to this plate. So these two plates separate the charges. Okay, so this static charge called electric field. So capacitor has ability to store electric field. So the ability of storing electric field is called capacitance. What is capacitance? It is the ability to store the charge carrier. Right? It is the ability to store charge, not to charge static charge. What static charge represents? Electric. So capacitance is the ability of the capacitor. So this is all about the capacitor. What is the formula? Epsilon A by D. Okay, now come to the point of understanding transition capacitance. Why transition capacitance? Because the reverse voltage keeps changing. If I increase the voltage, what happened to my CT? If I decrease the voltage, what happened to my CT? What increases, decreases? Reverse voltage. If increases or decreases, what happened to my CT? Whether increases or decreases. That is what we are here to study. What is transition capacitance? It is the capacitance exists during reverse bias. It is the capacitance effect at the junction exists during reverse bias. Take down. Increase in uncovered charge. Let's say, yeah, please complete this diagram. Please complete this diagram. A bar of chocolate have induced indium component, have heated higher temperature. Then what happened? The indium is come and join with the end region that forms alloy junction. What is that? ALLOY, alloy junction. What is this name called? Alloy junction, right? Alloy junction. What is the title? What is the title? Fusion junction. FUSION, fusion junction. Okay, alloy junction. So now the alloy junction now represents now this alloy junction. Listen, my dear students, to understand transition capacitance from the Millman book. Okay, in the Millman standard book, right? Right? Very standard. In the Millman they given. Otherwise, I could say take P and N type region, draw this, not like that, right? So in the Millman, they studied transition capacitance with the help of alloy junction, fusion junction, I mean, 4 5 decades ago, right? It is very long, right? Now take down P type region, N type region, not a semiconductor, right? P type, N type region, call it as alloy. Assume that both are have acceptor. This side donor, this side acceptor. So W, width of the acceptor will be wider and the width of the donor will be less. Again, the potential, right? Potential at this point is higher at this point and lower in this point. So what this says that there is a region have ions, right? There is a region called ions and there are uncovered charge. There are uncovered charge resting on both the sides. Now, increase இதுக்கு பேர் charge density called potential, POTENTIAL, potential. இது charge இந்த axis பேர் charge density எழுதுங்க. இதுக்கு பேர் என்ன? Potential. What potential? Electric potential. ஓகேவா? Exists at where? Exactly at the junction. Exactly at the junction. in uncovered charge increase இந்த டயக்ராம் போட்டுட்டீங்கன்னா ரைட்டா ரைட் இந்த ரெண்டு டயக்ராம் புக்ல இருக்காதுமா புக்ல இதான் இருக்கும் ஓகேவா இது just to understand increase in uncovered charge with applied voltage increase in uncovered charge with applied voltage may be considered as a capacitive increase in uncovered charge with applied voltage may be considered a capacitive capacitive effect. Now incremental capacitance CT given by incremental capacitance CT given by this topic belongs to unit number 1, right? I request everyone please write it on the page. There's a meaning for everything, right? Incremental capacitance CT given by capital C T is equal to modulus of dq by dV, where dq d suffix q is increase in charge caused by increase in charge caused by a charge caused by a change in dV. You know the simple, right? dq by dt simple adana person, okay? dq by dt dV in volt that is the current small I is equal to capital CT dV by dt. Capital small I is equal to capital CT dV by dt, change in voltage with respect to time. That is the amount of current across the alloy junction, across the fusion junction or alloy junction, ALLOY, alloy or fusion, FUSION, fusion junction. What I gave minus one amount of current across alloy junction or fusion junction is due to change in voltage is due to change in voltage dV in a given time, dV in a given time dt which results in small I equal to dq by dt, small I equal to dq by dt, right? Okay, now from figure this is the figure, right? What figure shows? Listen, this is figure. What they shows? A is the alloy junction, B is the charge density distribution across A, B and C, where small a shows 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 charge transition across charge transition or charge transition or injected minority carrier carrier across the junction. Right. B, small b, charge density distribution at junction. B, small b represents charge density, density, charge density at junction of of alloy junction of alloy. Okay, why I am calling alloy? Because indium is dissolved at elevated temperature. Indium dissolved at elevated temperature of or on the end region. Okay, one of the alloy junction. Third one enappa? P shows electric field potential of the junction. P வந்து என்னப்பா? Electric field potential of the junction. Next, figure 1 shows, or above figure shows the charge density as function of distance. Figure above shows the charge density as a function of distance from an alloy junction. Charge density as a function of distance from an alloy junction in which the acceptor impurities ACC, EP, TORS acceptor impurities TIES impurities acceptor impurity density is assumed to be much smaller than donor concentration. Much smaller than donor concentration. அப்படியே அதோட பார்த்துக்கலாம். Much smaller than the donor concentration. இங்க பாருங்க, இந்த width எப்படி இருக்கு? சின்னதா இருக்கு. இந்த width எப்படி இருக்கு? பெருசா இருக்கு. Acceptor ஓட width என்ன? Greater than the density. Got the point? Charge. You got the point? Listen. So what y-axis represents? Charge density. What x-axis represents? Distance from the junction. What y-axis represents? Charge density. What is x-axis represents? Distance. You see that in y-axis, Nd have higher density compared to Na. I'll repeat. Nd have higher density compared to Na. But in case of width, Na is greater than Nd. In general, what is capacitance? Capacitance C is equal to epsilon A by D, where epsilon is permittivity. What is called? Permittivity of the dielectric. Epsilon is the permittivity. What is A? Area of the dielectric. What is D? Distance. What is the distance between this? You got the point? You see that higher concentration with a lower distance, lower concentration with a higher width. Okay, you got the point now. Consideration. Since the net charge must be zero. The net charge must be zero. Thus, thus E capital N if NA is much lesser than ND, then WP is much greater than WN. The relationship between potential NA far less than ND, WP far less than WN. The relationship between potential and charge distribution, the relationship between potential and charge density, the relationship between potential and charge density is given by d dV square divided by dx square is equal to E capital N A divided by permittivity, where epsilon is the permittivity, where epsilon is the permittivity, where epsilon is the permittivity of the semiconductor, where epsilon is the permittivity of semiconductor, where epsilon equal to permittivity of the semiconductor, that is equal to epsilon equal to epsilon r dot epsilon naught, where epsilon r is the relative permittivity, where epsilon r is the relative permittivity of a dielectric constant, where epsilon r is the relative permittivity of the dielectric constant, and epsilon naught is the permittivity of free space, permittivity of free space, permittivity of free space. At x equal to 0, at x is equal to 0, or at junction, permittivity is equal to at junction epsilon I'm sorry electric field potential, right? Okay, at junction E is equal to minus dV by dt, electric field potential E is equal to minus dV by dt, that equal to 0, and also the potential at this point is equal to 0. Listen, x-axis represent distance, here y-axis represent charge density. Here x-axis represent distance and y-axis represent potential. At 0, what is the potential? At 0 is equal to 0. At somewhere it is equal to maximum. You got the point? At 0, the electric field is equal to 0. Because the flux from 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 positive ion terminate at flux from positive ion terminate at negative ion. Magavani, what is that? Okay, it's look like a x-axis. What is the potential at this point? Generally E equal to minus dV by dx, where x equal to 0. What is voltage at that point? Equal to 0. Why? Why this 0? Because what is this? P region. What is this? N region. What is this region? Dielectric. What is as? Positive ion, negative ion. What is dielectric? What is dielectric? Positive ion, negative ion. Okay. So okay. So the flux starts from positive ion and terminate at the negative ion. Where is flux? From positive to negative. Positive located in the N region, negative located in the P region, because these two are ions. And what is this? Charge. What is this? Charge. Majority carrier moving away from the junction. Next slide. Integrating the equation, integrating the equation 4, integrating the equation 4, V is equal to e to the integrating equation 4, they got V equal to E capital N suffix A x square divided by 2 epsilon at x. Next line, at equation number 4, integrating equation number 4, we have got this equation number 5. Integrating equation number 4, integrating this, we have got V equal to E N A x divided by 2 epsilon. At x is equal to at x is equal to at x is equal to WP approximately, understand that, or we assume that, what is the WP? Width of the acceptor. What is WN? Width of the donor. Assume that WP is equal to WN. Assume that WP is equal to WN. Then V is equal to VB. V equal to VB. Where VB is barrier potential, where VB is barrier height, where VB is barrier height. Now VB is equal to barrier height, VB equal to now the applied voltage, V, now the applied voltage V, now the applied voltage V. So what is now applied voltage? Because before that we understand there is no voltage at all, right? Initially at point equal to 0. While integrating we got V. What is VB? VB equal to barrier potential. What is V? Applied voltage. Now VB is equal to V naught minus V. What is VB? Barrier potential. What is V naught? Where VB is the barrier potential, V naught is the contact potential, and V is applied potential. VB is the barrier potential, V naught is the contact potential, where V is the applied reverse. Okay, ma'am. Next line. The thickness of the depletion region increases. The thickness of the depletion region increases with applied reverse voltage. The thickness of the depletion region increases with applied reverse voltage. Applied reverse voltage. Reverse voltage. That is if A is the area of the junction. That is if A is the area of the junction. If A is the area of the junction. A is the area of the junction. Area of the junction, and W is the width of the junction. W is the width of the junction. Then CT is equal to dq by dt. So that is equal to E NA into A W divided by dV. This is equation number 7. Equation number 7. Okay. From equation 6. Equation number 7. From equation 6. From equation 6. Modulus of dW divided by dV. Modulus of dW divided by dV is equal to epsilon divided by epsilon, right? Epsilon divided by E into NA into W. Hence CT is equal to epsilon A divided by W. Epsilon A divided by W.